In this video, we're going to discuss interrupts. We'll go over how they work and how to use them. And then in the next video, we'll talk about switch bouncing and how we can solve this different ways with debouncing technique. Okay, so interrupts are basically just a way that we can initiate some code or a subroutine by the hardware itself, as opposed to being called from the program or under the program control. All computers have some support for interrupts, but this is an especially important topic for embedded systems. In fact, this is usually called interrupt-driven programming, as programs for these devices are typically designed in such a way that most of the work in the application happens inside these interrupts, or we call them interrupt service routines. Okay, so there are two main ways that we can design our programs to access I/O. The first approach for accessing I/O is called polling. So let's do a quick example showing how we might write a program that's going to check if one of our switches is turned on. So I start off with a symbol here for my address for the switches, an arbitrary location which we picked when we were designing the hardware. And I'll put that address into the register X5. Now if I want to get the value of the switch, I'm going to do a load. And then let's say I wanted to check the first switch. So I'll do a bit mask here. I'll AND the value that I've got from that location with 1. Then maybe I do something else with that information. I have some subroutines or some other logic here that depends on that value of the switch. Let's say, for example, I run some other code if the switch is on. If it's not, then I continue. Okay, but remember, we have to be continuously checking the switch. We want to see if it's turned on, so I'm going to have to come back and reread the switch again. So at the bottom here, we're going to have an unconditional branch or a jump back to the load. And I'll just continue to do this until the switch is set. So this is what we call polling. And it's one style that I can use to access I/O. I'm continuously checking the input, reading that value until it changes. And so as you can probably guess, this can be wasteful in terms of performance and energy. What is my CPU doing? It's constantly reading when, say, the switches are not changing and doing this over and over, which we could also say is a waste of CPU cycles. So this is where interrupts come in. Rather than continuously polling or reading the inputs, we can let the processor do something else and wait to take care of the code that needs to happen when that interrupt changes until the hardware is signaled or interrupt that something needs to happen. So as I said, all CPUs have some form of interrupt support. Some are more complicated than others. With our Otter MCU, we'll be implementing a more simple but complete interrupt architecture. Okay, so regarding our program, there's going to be 3 main parts. And by the way, in 329, you'll do more programming of this style as well. So the first part is where we initialize this system. We set up the machine so that interrupts are enabled, and also the machine knows where to go when a particular interrupt signal is received. After the init, or the initialization part, then we get into the main code. This is typically an infinite loop where the processor is doing something. We could also potentially put the processor into a low power or a sleep mode when nothing is really happening. The third part is where a lot of the action actually happens for these interrupt-driven programs, and this is called the interrupt service routine. These tend to be short and look sort of like subroutines we've seen so far, with a couple key differences in their execution. So the main code is sort of like our foreground task, and when an interrupt occurs, it interrupts whatever's happening and will switch execution over to the interrupt service routine, the ISR. Okay, so the execution for an interrupt will look something like this. We start off, the machine is executing something, probably in its main code, and it will receive a signal from the hardware. This will trigger the control unit when it's ready to switch over to executing the ISR. But before it does that, it needs to save some state. This could be different types of architectural registers, but one in particular register that's important is the PC, because remember, after we finish the ISR, we need to come back to the location of the main program where we were currently executing before we were interrupted. We can then start executing the ISR code. And then at the end, we're going to restore any state that was saved and then switch back execution to the main program. In our machine, whenever an interrupt occurs, we're going to design it so that that currently executing instruction finishes. We then will go to the ISR, and when the ISR completes, we'll return back to the next instruction that hasn't started yet. Okay, so this is our modified Otter architecture with some additional support for interrupts. So the main piece that you're going to have to change is the FSM. And I've also posted on Polylearn the state diagram that corresponds to our interrupt, which is basically just adding one additional state. I've also provided you with this module called the CSR, stands for the Control Status Registers. This is essentially like another register file, but with registers that have special purposes for the machine. Architectures typically have different levels of access and state with different privileges. For RISC-V, the specification has a machine, user, and privilege mode. We're not going to get into these in 233, but we will include a couple of machine level CSR registers which are important for interrupts. And machine mode is the highest level of privilege, which is very common for embedded type systems. The CSR registers that we're going to use are MTVEC, stands for Machine Trap Vector, which is going to hold the address for the start of the ISR. So at the beginning of our program, we'll load that register with whatever address we want for the ISR. MEPC, or the machine exception PC, is what is going to hold the PC that will return to after the system has initiated an ISR. And then we have a couple registers that hold single bits for enabling if interrupts occur or not, and that's the MIE, Machine Interrupt Enable, and the MStatus register, which also has a similar bit for enabling registers. The MIE will be one that we can set from the software level, and MStatus, the machine status, will be set by our control unit. You can find more directions on this lab on Polylearn. But let's go over an example of writing a program that uses interrupts. Okay, so I'm first going to write some code for my ISR, my interrupt service routine. So in this example, I'll assume in the hardware that I've connected the switch to the interrupt signal. So when that switch turns on, it will trigger an interrupt. So in my ISR, actually what I'm going to do from the previous example with polling is whatever I had to do when the switch was set. Now at the end of the ISR, we're going to need to return, but I can't use an RET instruction and just jump to the address in the return address like we've done previously with subroutines. I also need to restore some of that state and also jump to the right location. I'm not going back to the return address. I'm going to go to what's stored in that MEPC register. So we can use the machine return instruction to load into the PC the value that we previously saved, or more specifically that the machine saved when it initiated the interrupt. Now in the main program, the first thing I'm going to do is init, or initialize, my machine, and that includes loading the address for my ISR into that special register, the MTVEC register. So we can use an instruction for accessing the CSR registers called CSRRW, or in this case I just need to write, so I'll do CSRW. And the value that I'll write into the machine trap vector, actually I need to load previously into another register, so I'll do a load address into the register T0, and I'll put the address for the first instruction that's in my ISR routine in that register. So then I'll write to MTVEC, the machine trap vector, so I'm setting up my machine so it knows where to go to when the interrupt occurs. We can then enable the interrupts by setting the MIE bit. And then after this point, now interrupts are enabled, and the machine, if an interrupt does occur, it will finish the currently executing instruction, change the PC to be the value in the MTVEC so that it starts executing the ISR, as well as saving the next instruction to execute into that MEPC register. So after the init and the main loop of the program, I'll just do an endless loop here. So you can see here the main benefit of interrupts here over polling. With polling, we had a loop where we were constantly reading the value of the switches to check and see if we were ready to do something yet. For this code, with interrupts, And the interrupt support in hardware, we're not constantly checking. In fact, the machine, when that switch is set, will trigger an interrupt and the machine will switch over to this ISR to handle doing whatever it needs to for that particular switch. And the processor can be doing something else, running some other code, or it could perhaps even be going into a sleep mode.